Now that you've learned about the classes of enzymes, which tells you about the general goal of a chemical reaction, we're going to learn about some of the strategies that enzymes use within those confines of the classes to catalyze the different types of chemical reactions. Here's a list of strategies that enzymes use to catalyze chemical reactions. We'll go through them individually rather than reading them off now. The first strategy is for the enzyme to use general acid-base catalysis. To start, let's think about what regular, plain old acid-base catalysis is. For regular acid-base catalysis, which would occur on the left, protons are transferred between a molecule and water to either protonate or deprotonate the molecule. In this case, oftentimes the protonated or deprotonated form of water is the acid or the base. General acid-base catalysis, which you see on the right, is when acid-base catalysis is performed by an amino acid side chain within a protein. So acid-base catalysis equals water, or sodium hydroxide, or HCl, whereas general acid-base catalysis comes from within a protein. They're not the same. Again, we can see on the left-hand side of the reaction, water is acting as the base in the acid-base catalysis, where on the right, a protein component is acting as the acid or a base in the acid-base catalysis. Take a minute to think about which amino acids would be good proton donors and which amino acids would be good proton acceptors. You can pause the video and maybe make a list, and then we'll look at some examples on the next slide. The slide here demonstrates exactly why we spent all that time memorizing amino acid side chains and pKa's. Here, all of the side chains with pKa's and whether or not they're protonated form or deprotonated form makes a good proton donor acceptor. Hint, the protonated form of the amino acid is a good donor, while the deprotonated form is a good acceptor. And whether or not the protonated or the deprotonated form is positively, neutral, or negatively charged depends on the side chain. But fortunately, you already know that from exam 1 and quiz 1. One thing that might stick out to you here is the inclusion of serine, because we didn't memorize the side chain pKa for serine. However, this is because serine has a pKa of about 13, so it won't normally be deprotonated under normal neutral pH conditions. However, the protein is capable of manipulating the environment around the serine to lower its pKa so it can be deprotonated during an enzyme reaction. The next strategy is covalent catalysis. In this strategy, the substrate, or an intermediate, is temporarily covalently bound to the enzyme, usually from a particular side chain acting as a nucleophile. In chymotrypsin, we'll see the full reaction later. Serine 195 is deprotonated and acts as a nucleophile to do covalent catalysis. The third strategy is metal ion catalysis, which is used by approximately 1/3 of all enzymes. This works by having ionic interactions between the metal and a substrate, or even the transition state. Frequently, metal ions are involved in oxidation reduction reactions. Some common examples of metal ions and enzymes that use them are shown here in Table 6-1. The last two strategies, proximity and orientation effects and transition state stabilization, are used by all enzymes. Proximity and orientation works by twisting the substrate into a constrained conformation so that the reaction proceeds faster. Here we have an example of an organic reaction that occurs on its own without an enzyme catalyst. The reaction speed is increased 10,000 times just by connecting the two groups, which eliminates the need for the two substrates to find each other in space. The reaction is then sped up by another 1,000 times by adding a weird-shaped group that constrains the two functional groups. This causes the reaction to go faster in order to relieve the strain inherent in the molecule. Enzymes achieve this by bringing the substrate and any other molecules that are needed into close proximity of each other in the enzyme active site, and then contorting the molecule in such a way that will further speed up the reaction. All enzymes do this, just in a slightly different way. The last strategy is again used by all enzymes, and so transition state stabilization and the proximity and orientation are the minimum strategies used by all enzymes. As a reminder, enzymes catalyze the reaction by stabilizing the transition state. This lowers the activation free energy and therefore increases the reaction rate. Transition state stabilization is key because if the enzyme were to stabilize the substrate instead, the activation free energy would become so big that the rate would actually slow down. Enzymes mold their active site to preferentially interact with the transition state rather than the substrate to encourage transition state formation to lower its energy and therefore speed up the rate of the reaction. I've told you that all enzymes use transition state stabilization, which is a pretty big claim to accept without evidence. How do we know this is the case? Well, one thing we can do is to feed the enzyme a transition state analog, which is a molecule that looks enough like the transition state to bind, but different enough that the reaction can actually be carried out. If an enzyme is inhibited by the transition state analog, it's binding the transition state. Oftentimes, transition state analogs make very good enzyme inhibitors for this reason, and sometimes they could even make good drugs. Another example is using a catalytic antibody. One can synthesize a transition state analog and inject it into an animal to produce an antibody against the transition state analog. And then that antibody protein, in theory, could catalyze the reaction against the substrate molecule just like a normal